Hello, everybody. Welcome to the Latin American webinar on physics. Today is our webinar 167 of the series. We have a long history of webinars. And today we have a very special guest to the law physics community, the Professor Óscar Zapata. He's from the University of Antioquia. And he got the PhD, the doctorate in physics in 2010 in the same university, the University of Antioquia. And since 2012, he is professor at the Physics Institute at that university. So, Oscar, welcome to Law Physics. The title of his webinar is going to be Dark Matter in QCD-like Theories with theta vacuum. And Oscar, welcome, and you can share a screen and start whenever you want.
Okay, thanks, Roberto, for this kind introduction. I'm very happy to be here, and I would like to thank to all of you for this very special invitation. So let me share. Okay, please confirm that you're seeing my screen. Okay, perfect.
Yes, we can say.
So, uh, as Roberto mentioned today I'm going to tell you about the impact of having a non-zero theta vacuum, a non-zero theta value in QCD-like theories, in particular, the implications regarding dark matter. This work has been done in collaboration with Camilo García Celi and Giacomo Landini at the Universidad de Valencia in Spain, and is based on this work is based on in this work and some work in progress. The So the outline of my talk comprises basically two main parts. Uh, some some kind of long introduction where I was going to discuss the same mechanism and the SIDM scenario. Then I will discuss the dark matter in QCD-like theories. The second part of my talk is about the theta vacuum in this kind of theories. In particular, I'm going to discuss the pion interactions and the cosmological and astrophysical implications. Finally, I will give a brief summary and present some outlook of our work. We have that the evidence for dark matter is abundant and compelling. We have evidence coming from different length scales, for example, from galactic scale to galactic rotation curves, from extragalactic scale, as for example, the Bullet cluster, and also from cosmological scales, as for example, the CMB anisotropies. This evidence is telling us that the dark matter uh, accounts for around 1/4 of the energy density of the universe. And if the dark matter is composed by particles, these particles must be massive for sure, neutral, almost neutral, and cosmologically stable. Despite of this evidence, we have the nature of the dark matter is still unknown. We don't know what is the mass of the dark matter particle, the spin, could be a scalar, a fermion, etc. We don't know its interactions, and and also we don't know the production mechanism. Among the long list of dark matter candidates that have been proposed in the literature, we have the winds that are the most well studied. The winds, basically, the idea behind this mechanism is that they reach thermal equilibrium with the standard model sector. Basically, this reaction takes place in both directions. So this means that the production and annihilation processes take place at the same rates. And the weak miracle is realized by considering electroweak interactions and masses around 100 GeV. With this kind of values, we easily explain the observed matter abundance, as we see here, for a weak cross-section, for example. In this case, the dark matter abundance is set by 2 to 2 processes when we have 2 dark matter particles in the final state and 0 dark matter particles in the final state, both with 2 standard model particles. So it's 2 to 2, it's a 2 to 2 reactions, both with 2 dark matter particles in the initial state and no dark matter particles in the final state. Despite of being an appealing mechanism, we have that it is not free of challenges, both from theoretical and experimental levels. For example, it may need some degree of fine-tuning to explain the correct dark matter abundance, and also the null direct detection results have led to more and more constraints. So, as an alternative to this mechanism, we have the SIM mechanism, the SIMs for strongly interacting massive particles. That this mechanism was proposed by Hodgdon et al. In 2014. In this case, the dark matter particle is the lightest particle in a nearly situated dark sector, and the dark matter abundance is set by number changing processes in the dark sector. For example, 3 to 2 processes where we have 3 dark matter particles in the initial state and 2 dark matter particles in the final state. In this case, the dark matter abundance can be easily reproduced for dark matter masses around 100 MeV, in contrast to the wind mechanism, where the typical masses are around 100 GeV. This these scenes, they are subject to constraints coming from cluster observations due to the elastic scattering of dark matter particles, 2 to 2 scatterings. So these kind of observations constrain this scenario. And a key ingredient of this mechanism is that the thermal equilibrium with the standard model must be invoked through some specific portal. So this requirement is, in some sense, model dependent. On the other hand, we have also that the collisionless cold dark matter paradigm is not free of challenges. For example, embodied simulations predict that predict universal halo profiles with large central density, in contrast to observations. For example, the simulations predict this kind of behavior with the density going as r to the -1, so alpha is equal to -1, in contrast to the observations that prefer a more a flat profile. So in particular, alpha almost 0. So this is the well-known Core versus Cox problem. And also this simulation also predict very massive Salerae halos in the Milky Way, which have not been observed. This is the too big to fail problem. These 2 problems can be mitigated or resolved by introducing at the end the baryonic processes into the simulations. However, there is also an appealing alternative to these possibilities, and this possibility is the SIDM scenario, self-interacting dark matter. In this case, this scenario allows for dark matter elastic scatterings, 2 to 2 processes in the inner regions, in such a way the central density is reduced and being compatible with the cluster observations. Concretely, this scenario requires a strong self-interaction in dwarfs. A strong self-interaction means that the cross-section over the dark matter mass must be around 1 to 10 centimeters squared per gram for dark matter velocities of between 10 to 200 kilometers per second. This is the typical velocities in dwarf. And must at the same time must fulfill the cluster constraints that impose that this same quantity must be less than 0.5 centimeters squared per gram, but for dark matter velocities of the order of 1,000 kilometers per second and above. So from these from these conditions, we have that self-scattering cross-section that decreases with the dark matter velocity for sure can lead to a better fit. And in particular, the resonant SIDM can do this in a very in a easy way through a resonant scattering. In this case, the 2-to-2 process is mediated by the on-shell resonance, and this cross-section receives an enhancement for dark matter velocities near to this VR velocity that is a parametrization being instead of that parameterizes the difference of between the dark matter mass and the mass of the resonance. So this scenario was proposed by Garcia Celia Morayama in 2018 and can successfully account for the required interaction. At the end, it requires a near threshold resonance with a velocity between 10 to the minus 7, 10 to the minus. So this is the typical values for this velocity to explain, to be compatible with this survey. Now we move to the the subject of QCD-like theories. So these kind of theories are based on a dark gauge group, in particular the SUN group, but the orthogonal and symplectic groups can also be used. In this case, we this this dark group involves NC dark colors and also NF flavors of Dirac quarks in the fundamental representation of this SUN color group. So with these ingredients, the Lagrangian is given by the kinetic term for the gluons, the kinetic term for the fermions, and the mass term for the quarks. Typically, the theta term has been neglected in the literature. So, and we have n flavors of Dirac quarks, so and with different from zero, all of them. So in the case of massless quarks, we have a global symmetry that is the product of these two SUN groups. And in analogy with the standard QCD, so this is to put it clear, we are invoking a extra QCD sector, the dark QCD sector. So it's not the standard one. So, however, in analogy, the strong interactions, the dark strong interactions confined at some energy scale lambda, which give rise to a fermion condensate, and in turn, this induces a chiral perturbation, a chiral phase transition, which spontaneously breaks this global symmetry and leading to the vectorial part, leaving the vectorial part as an unbroken symmetry. So this vectorial group is defined by through this kind of transformation. Good. So, but symmetry breaking leads to NF square minus 2 pseudo-Goldstone bosons, the pions, the dark pions, which are described by the chiral perturbation theory, leading to this, giving us this effective Lagrangian that comprises the kinetic term, the mass term, and the topological term known as the Wess-Zumino-Witten term. In this Lagrangian, f pi is the dark meson constant, which is related to the lambda scale through this relation. And this notice that this mass term, the quark mass term, break the global symmetry. However, for like masses, this global symmetry is still a good symmetry. So in that case, it is possible also to we can trust this chiral perturbation theory. And for the case of the general quark masses, we have that the um, the masses of the dark pions are given by this product B0 times the quark mass, where the B0 is related to the quark condensate. So the dark matter in this kind of theories it takes the form of a dark pion, where the relic abundance is set by the 3-2 processes, which are mediated by the Wess-Zumino-Witten term, that is a kinetic interaction that involves 5 fields. So in this case, this interaction leads us to a thermal cross-section that is velocity suppressed, where x is the standard parameter of the dark matter mass over the temperature. And as we can see, for typical values for the dark matter mass, the pion of 100 MeV, it's possible to explain the observed dark matter abundance. For sure, depending on the value of F pi. We have also that these pions can also interact via 2-2 processes that originate from this uh, interaction term in the Lagrangian. The corresponding cross-section goes as the dark matter, the pion mass square over f pi to the 4th power. And notice that this cross-section is velocity independent. So at the end, within this kind of theories, there is no possible to realize the SIDM scenario. In this plot, the y-axis represents the interaction constant, f pi, and the x-axis is the mass of the pion. The black points correspond to points explaining the dark matter abundance, of the dark matter abundance. The red line corresponds to the perturbativity limit. So this means that the region below this red line is not reliable. So the calculations are not reliable. And the dashed blue line corresponds to the border cluster constraint, meaning that this blue region is ruled out by this kind of observation. So at the end, as you can observe, this scenario is in tension with the bound from cluster of galaxies. So this kind of theories can explain the dark matter of the universe. However, this can be explained both in the zone where that is excluded by the bullet class observer. So now let's move to the implications of considering a non-zero theta term in the Lagrangian. So we consider as the SUN gauge group with NF flavor of Dirac quartz, and we add this term with theta being much more less than 1. We are going to consider the more general case of different masses for the quartz. And due to the chiral anomaly, we can perform this kind of transformations that moves this theta angle to this term and the quark mass to this new expression. So by choosing the particular charge assignment, we can remove the effect of a non-zero theta angle to only to the mass term. So at the end, the implications of this of a non-zero theta angle are in the quark mass matrix. So the pion interactions get modified uh, uh, in this way, where, as I mentioned, only modify the mass term. So the corresponding interactions are given by this Lagrangian, the new interactions, and notice that these new interactions involves a cubic interaction and a kinetic interaction. The cubic interaction is a new type of interactions that are not present in the case with a theta angle equal to 0. In contrast, this interaction is also present thanks to the Wess-Zumino-Witten term. But in this case, this term is not the corresponding cross section is not velocity suppressed. So at the end is wave is an wave. Is wave suppressed. Good. So we have new cubic interactions, a new and unsuppressed kinetic interaction. So the corresponding Lagrangian for the mass term is given by this expression, and as the dark matter and the mass of the pions scale as NQ times the energy scale, we expect that the meson spectrum is quite degenerate. So typically we can expect resonance. And notice also that dark baryons and blue balls have typical masses of the order of lambda. So this means that considering the mesons are the lightest of the mesons as the dark matter candidates, quite natural since the blue balls and dark baryons are heavy enough. Okay, so in order to illustrate the impact of a non-zero theta angle, we define two different benchmark models. The benchmark model 1 is fixed through NF equal 3, and we adopt the same notation as ordinary QCD. So the quarks, our quarks are up, down strange, but remember they are the dark up, dark down, and dark strange with this mass hierarchy. And as happened in the standard QCD, we have that the sharp pions, the kaons, and the neutral kaons are these linear combinations of the pions, pi 1, pi 2, etc. It turned out that pi 3 and pi 8 mix each other. So at the end, we have these two like mass eigenstates, pi 0 and eta, as happens in the standard QCD. And if we neglect theta square corrections, because we are considering theta values much less than 1, and the mass spectrum is given by this relation. So basically, this is what occurs in the standard QCD. So at the end, the spectrum, the pion spectrum, is uh, is given by this uh, is in this order. We have that the eta 0 is the heaviest one, while the pi 0 is the lightest one. In order to have non-relativistic resonant scatterings, we are going to consider only VR values less than 0.1, and because of that, MUS and MU divided by MS, this square mass ratio is a function of VR and also a function of this ratio, M up over M down. So at the end, we only have three parameters, VR and this mass ratio. And by fixing VR less than 0.1, the ratio of meson masses are fixed basically by RUD, as we can see here in this plot. So this in the y-axis, we have RUD varying from 0 to 1. And in particular for the sharp pions, the mass of the sharp pions can be related to the neutral pion mass as 1 plus delta, plus delta. Notice here that delta varies from 0.08 to basically 10 to the minus 5 for RUD values near to 1. So basically, at the end, we have that uh, resonance are quite natural within this scenario. And here, so I would like to highlight that eta acts as an unstable resonance, as we can see in the next slide. The second benchmark model is defined by the introduction of NF flavors with n of them being degenerate with a mass equal to m, and the remaining quark has a mass of the order of mu, and we choose this mass hierarchy. Due to this mass assignment, we have a Riemann-Sun symmetry where the NF square minus 1 pions organized as small n square minus 1 pions in the adjoint with this mass, 2n counts, n in the fundamental and n in the anti-fundamental representation with this mass and one singlet that is the eta, and in our case will be the resonance. For the particular case of 4 flavors, we have that the mass of the pion up to theta square corrections is given by this expression, and also for the eta mass. And notice that because VR is related to these masses, we obtain that VR is proportional to theta. So small values of theta lead to small values for VR. That is the condition for a non-relativistic resonance. And if we neglect theta square corrections, notice that these are the typical masses for the eta and the k. So these are our two benchmark models. So due to the cubic interactions, we have that all mesons are stable except the eta particle, and in the benchmark model 1, we have that it decays only into the neutral pion, to pi 0. And in the benchmark model 2, this resonance eta decays into all the pions, not the kaons, only to the pions. And the eta decay is controlled by eta square and some parameters. So now we move to the implications of for dark matter when we consider the theta and non-theta zero angle. So in this case, we have that the theta angle impact the dark matter production due to the number changing processes, for example, the 3 to 2 annihilations, and also the invert decay dark matter going into eta. As usual in co-annihilation scenarios, we have that all the stable mesons eventually convert to dark matter with a contribution to the dark matter relic abundance that depends on their masses. So basically, this is telling us that the contribution, for example, of the kaons, the contribution is basically negligible. And so at the end, for the benchmark model 1, we have that the dark matter is composed by neutral pions and the charged pions, because let's recall that the charged pions are nearly degenerate with the neutral one. The neutral. And for the benchmark model 2, the dark matter is only comprised by the pion. And keep in mind that we assume that the dark sector remains in kinetic equilibrium with the standard model, as usual in this kind of theory. So in order to determine how the kinetic equilibrium is achieved, we need to introduce a specific portal. So both that is part of our work in progress. So regarding dark matter, so the eta particle behaves as a catalyzer, inducing number-changing processes, such as, for example, this inelastic scattering, and also through this decay and this invert decay. And for values of VR less than 0.1 and values of theta larger than 10 to the minus 4, we have that this for these decays and invert decays are both active even after all number changing processes have frozen out. So they are, this means that are in equilibrium after this, for example, this process has freezed out. In order to explain all the dark matter abundance and be compatible with the constraints coming from Bole cluster, and also to explain to realize the ISIDM scenario, we consider this 3 to 2 process, both mediated by the eta particle, but we are going to assume that eta is real. So at the end, the 3 to 2 process is mediated by an on-shell resonance. So at the end, we have this inverse decay, 2 pions going into a 1 eta, and then eta plus 1 pion going into 2 pions. So from this assumption, because we are basically sitting in the parameter space where the resonance is achieved, we can solve the corresponding Boltzmann equations, and as we can see here, in the y-axis we display the yield of the dark matter. In this case, the yield of the eta particle, the yield of the charged pion, the neutral pion, and the yield of the total dark matter. The dashed lines are the equilibrium yield for the eta, while this red is for the neutral pion. And as we can see, the contribution in the after the freeze out, the contribution to dark matter, to total dark matter, comes from the neutral pion and also from the charged pions. But after some point, for some time, the charged pions annihilate into the neutral pions. So at the end, the dark matter is composed basically of a neutral pion. So during this time from here to here, then the dark matter is composed by neutral and charged pions, but after uh, theta equal 1,000, we have that our matter is composed only by neutral pions. And by assuming the so since we are in the parameter region where these processes are still active, uh, they allow us to simplify the corresponding Boltzmann equation to the two Boltzmann equations to one single Boltzmann equation that is controlled by this thermal cross-section that is independent of the theta value. So at the end, the dark matter abundance is set by S wave two processes. So basically, the eta plus pion going into two pions. So with this in mind, we try to establish what is the Biot parameter region that is compatible with all the constraints. In this plot, as usual, the y-axis represents f pi, where is the interaction constant, and in the x-axis we have the dark matter mass. This gray zone is excluded by perturbativity, while this upper gray zone corresponds to an overabundant so it's represents an overabundant region. So it's not possible to explain the observed matter abundance. So it's excluded by the Planck observation. And the blue region is excluded by the bullet cluster observation. So at the end, the viable parameter space is this white region, and these lines correspond from one specific value of RUD. So at the end, for one specific mass spectrum, pion mass spectrum. These results are independent of VR as long as the small dependence of them on the masses on VR and theta are neglected. So basically, it's independent of VR. This benchmark point is the one we are going to use, that we use to illustrate the SIDM realization. So for the benchmark model 2, as I mentioned, basically the dark matter is only composed by pions because the yield of the kaons is Boltzmann suppressed due to the difference on mass. And in this case, due to the larger number of degenerate pions, the dark matter abundance is reproduced in a parameter region in tension with the cluster observation. So it's not possible to be compatible with the Planck constraints and the Boller observation. However, this suggests that the dark matter must lie in a small representation. So at the end, if we break this degeneracy of the dark quarks, it is possible, maybe possible to explain the dark matter abundance and be compatible with the cluster bound. So this is also a work in progress. But for this benchmark model, it's not possible to be compatible with the cluster bound. So regarding the astrophysical implications, we have that the new interactions mediated by the theta angle also induce two processes, in particular resonant scatterings. And for the case of velocity, dark matter velocity of 100 kilometers per second, it is possible to have, sorry, so for dark matter velocity near to VR, it is possible to be compatible with the bullet cluster constraint. Let's remember that the bullet cluster constraint takes place at velocities around 1,000 kilometers per second, but velocities around between 10 to 200 kilometers per second, the SIDM scenario requires cross-section between about 10 to 100 centimeters squares per gram. So with this, in this case, with this line, it's possible to realize the SIDM scenario. This is for the benchmark model that I have shown, for the value for theta equal to 3 to 10 to the minus 3. So finally, I arrived to my conclusions. So we have pointed out a new production mechanism for dark matter in QCD-like theories with a non-zero theta angle. So this requires a resonance that mediates two to two processes, in particular the 3 to 2 mediated by first inverse decay and then through this inelastic scattering, and also requiring DR less than 0.1. The variable parameter regions can be compatible with cluster observations as long as theta is larger than 10 to the minus 4. So we require a minimum, there is a minimum value for theta in order to realize the SIDM scenario and also to explain all the dark matter above. And finally, this theta, so we also have this theta-induced scatterings might address the apparent small-scale anomalies of the collisionless cold dark matter paradigm. So this means that it's possible to be compatible with the Planck constraints without explaining this small-scale anomaly. So it's, I would say, optional. It's up to you. And finally, these theta-dependent effects are quite generic features of QCD-like theories. So this is also a subject that is under evaluation for bias. Finally, I would like to give some outlook of our work. So we want to go beyond SUN gauge groups, for example, to consider the orthogonal and symplectic groups. This is, in some sense, can be easily achieved. The next thing is to address the standard model portal. This can be realized by introducing identar photons, action-like particles, or vector meson. So these kind of portals have been discussed in the literature for all these QCD-like theories, but with a zero theta angle. So this is also work in progress. So as a third thing, I would like to speculate of the possibility of the gravitational wave emission due to the chiral phase transition in the dark sector. And I would like to highlight that some studies have pointed out that there is a phase transition, a strong phase order phase transition with a critical temperature of the order of 100 MeV. And this is quite appealing since this is related to sub-millihertz band, that is the one associated with the PTA signal. And finally, since we have a new term that violates the CP symmetry, it will be good to explore the possible connections and implications for the matter antimatter. So thanks for the attention.
Thank you very much, Oscar. It's very interesting, the topic that you talk about. So before to go into the question round, I will tell to the people that is following us in the YouTube transmission that you can write the question there in the chat, and we we will address the question to Oscar as soon as you post it. So let's start with some question from the audience. I don't know if some of you guys has a question for Oscar. Otherwise, I can. Also, I have one, a couple of ones. Well, yeah, I go. So, okay. I was wondering, Oscar, in this scenario with an SUN 2 or 3, do you still have the expected asymptotic freedom? I mean, would be the asymptotic freedom play a role in the early universe before the formation of this condensate of dark pions and stuff? I don't know, might help in the thermalization. I don't know, because
So at the end is we have some quarks that at the very beginning they are free particles that interact with each other. So then they confine, as happens in the standard model. Okay, so in order to, for example, modify to some extent the cosmological history, you need to, for sure, to introduce the portal. Okay, so without the portal, I will say there is no any particular effect on the cosmological history. Besides that, you are obtaining a relic, a dark matter relic. Okay, so the thermalization is achieved through this standard model portal. Okay, and for these QCD-like theories with that zero theta angle, these kind of portals, the dark matter implications are not spoiled. Okay, so this is a very interesting point. For sure, you have to take into account all the interaction and possible effects such as dark matter decays, etc. But it's possible to be compatible with all the constraints, even if you consider the portal.
okay, yeah, because I'm wondering, because I mean, I ask because I remember that in cases when, for instance, when one is studying the early universe in the standard model case, you have this spike of number of degrees of freedom when the all the meson forms because of the condensation. So I would expect that similar effect you would have at a different epoch in the history of the early universe, because
Okay.
in principle your scale is different from the QCD one. I mean, because the couplings are different. So, and I don't know if there are questions from Walter or Joel, otherwise.
I have a quick question. It's probably very simple. Regarding the theta angle. So of course, if you have I mean, the same way that we wonder what's the origin of the theta angle in QCD, if you have given a thought about how you set a non-zero theta vacuum for this, and then depending on the mechanism that you use, if you can have some topological effects, some topological defects like, I don't know, domain walls or strings or things like that, that this can give you some signature.
Yes, so I don't have any special comments about that because we just focus in realize the dark matter abundance with this kind of theory. But for sure, it will be good to explore what that kind of implication. So non-topological effect, topological effects.
So I have one because so I enjoyed your talk very much. But I'm wondering about the testability of the model, right? Because this is like, okay, a separate sector and la la la. So the main concern is how do you know, right? So I guess this depends extremely on the portal and how you actually get the thermal equilibrium, no?
Right. Yes, please go ahead.
No. So I was wondering, for instance, if you will get via the portal, you will get your pions to decay into standard model particles so that they could maybe be produced in a collider, or eventually.
Right.
I don't know if you've looked at this thing. Sorry.
Thanks, Joel, for the question. It's a very good point. So up to this point, there is no any, for example, particular signal regarding colliders, direct detection, etc. However, since we need to introduce this portal, depending on which kind of portal, you have different signals. For example, you can have a decay of these dark mesons into standard model particles that can be looked for in colliders. So depending on the standard model particles, so at the end, some specific signals that can be proved appear. So at the end, my answer is again depends on the which kind of standard model portal are you introducing. But yes, there are some signatures, but again, with no standard model portal, so there is no possibility to prove this scenario in colliders.
Thank you.
Thanks. Good.
So I don't know if let me check just in the in YouTube we still don't have any question, but I have a question really. It's in the same line that Joel was asking. So in the sense, since this model is since it's a strong interactive massive particle simp, would you expect the for instance the stability in the case of dark matter stars or something like that, because they are gonna be easier to get clumpy in the, I mean, when you have just dark matter stuff, not interaction with the star itself, but just in the, yeah.
Okay. Good point, Roberto. Thanks. So yes, for sure, it is depending on how strong is the interaction rate between the matter particles, for example, the 222 processes. It is possible to for example, compact objects, or even going beyond that. But that is again part of is beyond our scope in this moment. But yes, it is possible to within this scenario to form compact objects, dark compact objects. Yes. So in that sense, the astrophysical observations can make prove this scenario. However, again, is I would say in some sense model dependent, because you have to tune the elastic oscillation in order to guarantee the formation of this compact object.
Yeah, thanks. Walter or Joel, do you have question for Oscar? So
still on the thing of the portal. So can the portals eventually tell you if the theta term is present or not?
So, for example, if you introduce U1, dark U1, so this means that you are introducing a hidden dark photon. So the theta term is independent of this U1. So the theta term is still there, is still present. Okay. For vector mesons, the same happens the same. So the vector mesons, so we are meaning that you are going to consider, for example, heavier resonances, and then you can achieve the thermal equilibrium with the standard model. So in that case, the theta term is also present. For action-like particles, so in this case, since you are assuming, you are introducing an axiom particle, so in some sense you are removing the theta term, you are trading the theta term by the action. Okay, so in that case you have to check what are the implications. But for sure, you can say you can also consider extra action-like particles. But I would say for the simplest case, that is introducing an extra U1 dark gauge symmetry. So the theta term is also present there. It's still present.
Okay, super.
Okay, thanks, Joel, for the question.
So, okay, I was wondering, I mean, I have another question because also with because since in this kind of groups, SU beyond 3, you have a large number of gauge boson. Do they modify, kind of contribute to the invisible dark radiation budget of the universe? I mean, I know that this is small, the deviation with the effective number of neutrinos, but since you are going to have a lot of relativistic particle in the going around until the moment they become non-relativistic, but yeah, I don't know if there will be other signature at the cosmological level, even though they are completely a part of because there are still there is no portal.
Yes, so the idea is this extra species to contribute to the dark radiation. So in order to, so I would say it depends up to some point on the portal. So how you equilibrate, thermalize both sectors. But in principle, yes, they may contribute to this dark radiation. And yes, but you have to be compatible with the measurement at the Big Bang nucleus, BBN temperature, basically. That is the constraint. Okay.
Okay, thanks, Oscar. So let me just check if there is some question in the YouTube. No, for the just meme of distraction, say hi. But yeah, it was very interesting. The webinar we're almost going to the time, so we are gonna unfortunately we have to finish the transmission. But for all the people that are following the webinar, next week we're gonna have another webinar by if I'm not wrong, Philip Lynch. So, but anyway, you can see all the previous webinar, and this webinar is gonna be in our YouTube channel, and you can follow us, the news in the social networks that we have, or in the Google Groups mailing list. And thank you again, Oscar. It was a pleasure to have you here in the webinar series, and see you around in the next opportunity in the law physics webinar cycle. Okay.
Thanks to you guys for this kind invitation and for all the attention to the audience.
Okay, thank you.